Okay, now it's 8:30. I guess we can get started. So, hello everyone. Welcome back to the second day of the IWoAT 2022 summer school. Today we will have 3 lectures. The first one is another overview lecture, and it will be on the topic of higher category theory. And then we will continue from where we left off yesterday and have the second chromatic lecture and the second lecture on infinity categories. So the speaker for the opening talk today is Professor David Gepner from Johns Hopkins University, and he will tell us about some introduction to infinity category theory.
All right, well, it's an honor to speak at this summer school, and I hope to cover a good amount of stuff, but on the other hand, I don't want to go too fast. So if you feel like I'm going too slow or too fast, please feel free to voice an opinion. So maybe the question that this talk is centered around to begin with is just, why would we want to do infinity category theory? What advantages does it give us? And I think that probably most everyone knows what the answer, or at least the supposed answer, is supposed to be, that while higher categorical structures, they arise naturally. And well, let's say in, algebra, you have homotopical algebra, derived categories. Those are examples. Geometry, you have sheaf cohomology. You have manifolds and cobordisms. Other applications from algebraic geometry like elliptic cohomology or K-theory. Even in mathematical physics, and probably other areas of mathematics, number theory, for example. So they come up all over the place. However, in practice, what we don't have is strict compositions between categories that are enriched in spaces. The way that these things come up is usually, even if you even have a mapping space at all between two objects, is probably only well defined up to homotopy. And if for some reason it's well defined up to isomorphism somewhere, then it might not compose properly or associatively. So we need a formalism that allows for flexibility in this. So the formalism is, of course, going to be quasi-categories or Joyal-Fibrant simplicial sets. But let's step back for a minute and take what would be the naive model, which works and gives us some insight into infinity category theory. We'll take well, in this case, it happens to be a Quillen model category. Of simplically enriched categories. So categories that are enriched over simplicial sets, where the monoidal structure is the Cartesian product. And this is written, I'll use higher topos theory notation because this talk is really just a summary of the first small bits of that book. But we'll call it cat sub delta. Here, simplicial sets, the thing that's it enriched is, these things are enriched in, we'll write set sub delta. And this is, of course, functors from delta op to set. Okay, and we have a good notion of weak equivalence here. We can talk about functors which are homotopically fully faithful, in the sense that the mapping simplicial sets between any two objects only have to be a weak equivalence in the Kahn model structure, have to induce them on. So if C is such a thing, we'd ask for any pair of objects, say S and T, maps in C from S to T, and right, and we have D and we have a functor between them, F, then we can ask for this to be equivalent to maps in C from F of S to F of T. That's what it means to be homotopically fully faithful if this is for all S and T in the category C, and homotopically essentially surjective means for all objects in the target of the functor, I'll call it T and D, there exists an S in C and an equivalence, it doesn't have to be an identity, from F of S to T. So everything's hit at least up to an equivalence in the category. Okay, so the fibrant objects in the Bergner model structure on this category, where these are the weak equivalences, are simplicity enriched categories where all the mapping simplicial sets are Kahn complexes. But it's important to note that typically things are not cofibrant. And that's a problem. So there's not a good exponential in this category of simplicity enriched categories. Of course, there is one. There is a simplicity enriched category of functors between any two, but it is not typically homotopy invariant in the weak equivalences. It's easy to arrange for your categories to be fibrant. That just means they have Kahn complexes as mapping spaces, but the cofibrant condition is difficult. So we need to loosen this up. So how could we do that? Well, recall that there's this functor called the nerve from categories to simplicial sets given by the nerve of C in degree n is just functors from, all right, n in braces for the ordinal. I'm thinking of it as a poset and therefore a category. So I'll write it like that. To C. That describes C as a simplicial set, and this functor is fully faithful. So we embed categories into simplicial sets. Well, we can, in fact, extend this to simplicity enriched categories. So let me call this the nerve now, and it restricts to the one that we had before. By now we want to loosen up the category we called N to make it less strict. So how do we do that? We can send instead, so this is sending, so I should have mentioned this is a right adjoint functor. Its left adjoint is just determined by where delta goes in cat, and so this is determined by the functor from delta to cat that just sends n to this category that I just wrote down. So we want to loosen this up by sending it somewhere in simplicial categories, and then the functor which collapses a simplicity enriched category to just an ordinary category by taking pi 0 on the mapping objects, that's the homotopy category functor. The homotopy categories of where we send the objects of delta now to should be the same as the ordinals, but we're going to loosen it up by sending this time delta n to this different version where I'll still write the same sort of skeleton here. But for example, there's a different map from 0 to 2, not just the composition of the map from 0, 1 to 1, 2. And it's just saying we can go from 0 to 2 directly. And there's a natural transformation between that and the map 0, 1, 2, which goes to from 0 to 2 in 2 steps. And we can similarly do the same thing. We can go from 0 to 3 by, well, going in 3 steps, 0 to 1 to 2 to 3. We can do it in 2 steps, go from 0 to 2, then to 3. We, have the same thing going on here, and etc. What this means, if you spell it out, is that, well, the maps from any 2 successive things are what they should be. But if you want to go multiple steps away, for example, from 0 to 2, there would be the option of going directly or passing through 1. And you get a copy of delta 1 as the mapping simplicial set here. If I wanted to go from 0 to 3, well, I could do that either directly in these 2 steps or in 3 steps. And I get a copy of delta 1 cross delta 1 as the mapping simplicial set, etc. In general, you can imagine what the formula is. Maps between I and j are, well, they're empty if j is greater than I. There's a delta 0 if they're equal, because there's just one map. And there's delta 1 to the j minus I minus 1 copies. Whoops, I meant less than here. If j is greater than I. So this defines now, by knowing where each representable simplicial set goes, what simplicial category it goes to, you can work out the composition here. This then defines a nerve functor from simplicial categories to simplicial sets. And it's a theorem of Lurie, and many of the theorems that I advertise in this talk will be due to Lurie. Some of them won't be, and some of them are also based on other theorems in ordinary category theory. But this is a very special one because it's describing even the, how we can model infinity categories to get started with this whole program. So it says that this nerve functor from simplically enriched categories to simplicial sets, well, it's not directly fully faithful like the other one was, but it's going to be fully faithful up to homotopy, and is even going to be essentially surjective up to homotopy if we give the right definitions. So this is a right Quillen functor from the Bergner model structure on simplicial categories to the Joyal model structure on simplicial sets. So and I should describe what this means. I said some words about the Bergner model structure before, but the Joyal model structure, as probably everyone knows, the fibrin objects are the quasi-categories, the ones that have inner horn liftings. And the weak equivalences are, well, they're transported, or they're detected by the adjoint. I didn't write what this adjoint was. The left adjoint here is written usually like a Gothic C bracket. They can just be detected by that. So they're homotopically fully faithful and essentially surjective. So I'll just write that as before. Okay, so this tells us that the naive idea about just having simplicity enriched categories, or really the fibrant objects, so categories enriched in Kohn complexes, is a perfectly good model for infinity category theory, as we tend to think of it in terms of quasi-categories in the Joyal model structure. So, however, the Joyal model structure has a huge advantage, or maybe multiple advantages. It doesn't have every advantage, but it has lots of advantages. And the first one is just, it's a lot easier to specify a simplicial set than a simplicity enriched category. So the amount of data that you're carrying around is much less. But secondly, there's the exponential is homotopically well behaved. So in simplicial set, if C and D are infinity categories, which just means that they're Joyal fibrant, although I'll start maybe saying infinity category for just the structure independent of the model, possibly at some point. If they're Joyal fibrant, then the category of functors from C to D, this is just the exponential. This is homotopically it's well behaved. Sorry. Meaning it's invariant in weak equivalences in the source and the target. So it always computes the right thing. And it's just the exponential of simplicial sets, which means that the prime tool that we have in category theory, which is the formation of the functor category, is very well at our disposal. It's something that we can work with directly in this model structure. Okay, so it's basically combinatorics. And to illustrate that point, I want to now talk about some basic instructions. So joins, slices, mapping spaces, and limits. So the join, this is an underrated operation in category theory. It's something that really comes up frequently. But how do we think about it on simplicial sets? Well, we define a monoidal product on simplicial set by, well, first we do it on the representable ones. It's written star. It's called the join. And what we do is we join the two things together. Think of M as corresponding to this ordinal, delta M is corresponding to this ordinal, and delta N is corresponding to this ordinal. I wrote it like that before. Then what this should be is you just make an arrow from M to the new 0. So it's 0 to 1 to, well, we get to M. And then, well, we want to get to the new 0. I'll write. So the 0 in the sequence 0 through N becomes M plus 1. And we get up to M plus 1 plus N, like that. So what this is the simplex delta M plus 1 plus N. And then extend this to all of simplicial set by colimits. In other words, x star y is just going to be the colimit of all M simplices mapping to x and all N simplices mapping to y of this join, which we just defined. So this turns out to be a monoidal structure. It's not symmetric. It's antisymmetric specifically. That's a good exercise. And the utility is that it defines for us all of our over categories and under categories and comma constructions. So if f from D to some infinity category C is a functor, which I might think of as a diagram in C of shape D, and then I can talk about objects of C over or under this diagram, that's the comma categories. Then I'm just going to talk about the slice category, the over category. Then C over F, the slice of C over F. Usually slice refers to just the case where D is a point, so you're talking about a single object, but you can talk about it for a functor too. Has, well, I need to give you a Joyal-Fibrant simplicial set, so I need to tell you what its n simplices are. And this is easy to do. Its n simplices are all the things that look like delta n joined with D mapping to C, except that, well, now there's a map from D to C, which is F, which we already specified. And there's a map from D to delta n star D, which is canonical because, as you can see, the unit of the join is going to be the empty simplicial set. So this is just D again. But now we have a canonical map like that. So it's functors from, or simplicial set maps from delta n star D to C, which restrict to the given map F from D to C. So in particular, if D is a point, which I'll just write like that, F is just then an object of C. And definition, an object F of C is terminal. Oh, I can't define this yet. Hold on. I forgot to define mapping spaces. I'll come back to that in just a minute. So, yeah, actually, I was going to do this in this order because I was going to define the left Homs and the right Homs, and those are use the slice categories. But, well, what I should have said here, though, is that C over F is just the usual slice of C over the object F. And it's what you think it is, an n simplex of this is exactly an n plus 1 simplex of C, such that the final vertex is F. Okay, I was going to use this to define the R Homs and the left Homs, but in the interest of time, we'll do just the symmetric one, which is definition. So this is a good philosophical point. Because infinity categories are just simplicial sets satisfying lifting conditions, you're not specifying a priori the mapping simplicial set between any two objects. You have to extract that. And there's many ways to extract it and get an equivalent Kohn complex. And this is just one of them, one of several different ones. So this one is maybe the easiest to conceptualize, though. So if C is an infinity category, and we have two objects, S and T are objects of C, then map in C from S to T. This is supposed to be a Kohn complex. It turns out to be. This is exactly the fiber in the strict sense of the category of functors from delta 1 to C. So that's the arrow category of C. So it's all those arrows, which when you restrict them to the boundary, well, this is just isomorphic to C cross C, because after all, this is just the simplicial set exponential, and boundary of delta 1 is 2 points. It's the fiber over ST in here. Literally the fiber. That's why we can show that this has Kohn lifting. So it's a Kohn complex, and that gives a model for the space of maps in C from S to T. Okay, so now we can define what it means for an object to be terminal. An object T in C is terminal if for all other objects, the mapping space, however you want to construct it, there are other ways, like I said. Well, that maps down to the point because it's a space, and simplicial sets, or, you know, either simplicial sets or spaces have a terminal object, the point, if this is an equivalence. So in other words, if these mapping spaces are contractible, whenever you map into T, there's a contractible space of maps. That's what it means to be terminal. You might say we should have called it homotopically terminal, and we maybe would if C were a simplically enriched category, but we're working now, we're thinking intrinsically to infinity categories, so we're just going to call it terminal. So now we can define limits. They just pop out. So definition, let f from D to C be a functor of infinity categories. And this just means a morphism of simplicial sets that happen to be Joyal fibrant. Then a limit of f is a terminal object of the slice over the diagram. So objects of this infinity category you can think of as cones on F, and we're asking for the last one, the one that's closest to F, actually the vertex that's closest to F itself, the limit. Okay, so maybe it's worth saying, for example, if C is a simplicial category, and that just means simplically enriched, then, well, because of the enrichment, there's a canonical notion of Bousfield-Kahn style notion of homotopy limit and co-limit. And what happens in practice is that homotopy limits or co-limits in C are, well, they compute, they model or compute co-limits in the nerve of C. Maybe we should make C a fibrant simplicial category, because then we know that the nerve of C will be a quasi-category because N is a right Quillen functor. So that's the relevance of homotopy limits and co-limits of spaces and spectrum and other types of structures as building. homotopy limits and colimits in the infinity category, which is the nerve. There's some background noise. Can everyone check that microphones are off? Okay, so I want to talk next about fibrations in infinity category theory. That's the important topic. Maybe the point of departure for that is this nice fact in sets, or you can upgrade it to groupoids if you want. So let me call this fibrations. So if, just by way of introduction, if we have a set S, then a set over S, because S is just a discrete set, is exactly the same data as a functor from S, and I'm going to write an op here for future reference, even though it's just a set. So S op is just S again. Because a functor from S or S op to set is just a set for each element of S, which is exactly what a set with a function down to S is via the fibers. So if I have a functor F here, this goes to the Grote construction on F. Which all that is the set of all things that look like an element of the set and an element in the functor at that point. So let me call this X. X comes equipped with a map to S because, well, S is the Grote construction on the point, the constant functor at a point, and any such F admits a natural transformation like that. So we get a projection map P from X to S. So this remains true. One can show it's basically classifying space theory. We'll call it that. So that the same is true. Oh, I didn't define this yet. So I'm going to use the notation infinity groupoid, but I realized I didn't define it, so I will. These are presheaves on S, contravariant functors from S to the infinity category of infinity groupoids. Well, if I have such a thing, I can take what's called in higher topos theory the unstraightening, but it's a specific model for the Grote construction if we had a higher categorical definition of that. And well, it's the same thing. It takes a functor to the category now of all pairs where we have S as an element of S and X as an element of F of S. I'll say something more about this in a minute. But this goes to a certain subcategory of infinity categories over S. It's not a full subcategory. It's the infinity categories over S, which are Cartesian over S, and the Cartesian maps between them. These are called Cartesian fibrations. And there's an intrinsic definition of them that's not just what makes this an equivalence. So it's a useful theorem. Oh, and because it's groupoids, I really should have said right fibrations. Those are Cartesian fibrations where all the fibers are actually groupoids instead of categories. Okay, so to make this rigorous, we need to know what infinity groupoid means. And this I'll just take to be the nerve of the simplicial category of Kohn complexes. Here, Kohn is a full subcategory of simplicial set consisting of the Kohn complexes. And it's a fact that if I have two Kohn complexes, then the simplicial set of maps between them is again a Kohn complex. So it's a simplicial category that's enriched over itself. I can take the nerve of it and I'll define that to be infinity groupoids. What about infinity categories? That has a similar definition. I take the nerve of the simplicial category of quasi-categories, but here quasi-categories, well, it's also full in simplicial set, except I don't want that to be the simplicial structure. I take all the quasi-categories, but here the simplicial set of maps from C to D is the maximal Kohn complex inside the functor category. And well, it is a fact that if I have two quasi-categories, their exponential is a quasi-category. And so I can just take the invertible morphisms inside that quasi-category. That gives me the maximal Kohn complex. Okay, so I think that makes most of these terms defined now. But this just follows from classifying space theory, because if S is a Kohn complex, then being a right fibration over S is really no condition from the point of view of inside the category of infinity categories. So this is just the same as groupoids over S when S is an actual infinity groupoid. So this fails if S is not an infinity groupoid. There, you really need to distinguish the, here, let me do it in better generality. Instead of mapping just to groupoids, we'll map S, which is an infinity category. We can map it now to the infinity category of infinity categories. If we take the Grote deconstruction on that, we get what's called the Cartesian fibrations over S and the morphism of Cartesian fibrations over S. So this is a theorem of Lurie. Now I'm about to tell you what a Cartesian fibration is, but it's a simple condition that, as you can see, because of the theorem, picks out which maps of infinity categories X to S. So the moral, in case you're wondering why I'm talking about this, P from X to S is a Cartesian fibration based on this theorem, if and only if the thing which sends an object to fiber over S is functorial. So I'm viewing it as a functor from SOP, so contravariantly. Functorial in S. So intuitively, that is what a Cartesian fibration is. It's exactly those maps which correspond in the same way that categories fibered in groupoids and pseudofunctors correspond in classical theory. These Cartesian fibrations pick out exactly the functors. But there's an intrinsic definition, and it's the following. So I'm gonna give you the internal version of this and not worry about the thing actually being a Joyal fibration. I'm just thinking of maps inside now the infinity category of infinity categories. So definition, a map P from X to S in cat infinity is a Cartesian fibration if every map, say F from S to T in S, and so maybe I should say for every map like that and every object Y in X, there exists a, well, I'll just call it Cartesian. You might call it P Cartesian if you want to emphasize that it's relative to this particular map P. There exists a P Cartesian lift of F to Y. What does that mean? In other words, a map G from X to Y upstairs in X such that, well, P of G is F. So in particular, P of Y had to be T. And now the slice X over G, that maps to something over the target of G, just by forgetting some stuff, cross over S over T with S over F. So if I have an object equipped with a map to G, in other words, let's say W here, then I can just, I mean, this is already part of the data because it's really a two simplex, but I can forget to just this edge and I get a W over Y. I can project that down, I get something over T, and I can project down all of G to get something over F. And it's saying that X over G is actually equivalent to that. Oh, I didn't write is equivalent there. Okay, so there's lots of other ways of phrasing this, but this is the usual notion of Cartesian morphism or Grote fibration from, say, stack theory. I mean, one of the main examples is you take the category of vector bundles over manifolds. This is a Cartesian fibration. Because vector bundles pull back. You have the upper star functor, and that gives you your Cartesian lift. Okay, so stacks, any stack in the traditional sense, pre-sheaf of groupoids, or sorry, sheaf of groupoids or sheaf of categories, even sheaf of infinity groupoids or sheaf of infinity categories, those are examples of Cartesian, or that after you unstraighten them to a actual functor from X, the Grote construction, down to the base, that then those are Cartesian morphisms because you have pullback. So I want to point out that there's a universal. So I guess I should have said there's also a notion of co-Cartesian fibration, which is just the dual. I replace all the slices over G with the, instead of the over categories, I work with the under categories. Those are just coming from joining on the other side. That gives me a notion of co-Cartesian fibration. And it just so happens that it's somehow easier to describe the universal co-Cartesian fibration. You can dualize it to get the universal Cartesian fibration. But let's just talk about this. There's a universal co-Cartesian fibration. And that's if I apply the Grote deconstruction to the identity functor of cat infinity. That gives me something over, well, if I apply the functor from cat infinity to itself, which sends everything to the point, well, this is cat infinity again. And well, there's not really a name for the thing which appears on the left, but it is sort of the, it's almost like this co-slice over the point, except it's the collax co-slice over the point. In other words, functors don't have to preserve the base point. They only have to preserve it up to a map, up to a morphism. Okay, this is just because of the straightening unstraightening correspondence equivalence up here. Again, Lurie calls this correspondence straightening and unstraightening. The straightening functor takes a Cartesian fibration and straightens it out to an actual functor. The unstraightening takes a functor and just regards it, sums up all the fibers to get a co-Cartesian fibration over S. Okay, just pointing out that it's an instance, all co-Cartesian fibrations are pulled back from this universal one, just because any map from S to cat infinity factors through the identity functor of cat infinity. Because of this, and the equivalence between cat infinity over S Cartesian fibrations. So I didn't say what a morphism of Cartesian fibrations is. Those are morphisms which preserve the Cartesian lifts. Because this is equivalent to the functor category from S op. Oh, I should have done the co-Cartesian version. That would look like this. We see that any because a functor from S to cat infinity factors through the identity, any co-Cartesian fibration is pulled back from this universal one. So this was the functor classifying it. And well, we have the universal one. So this is really the generalization of classifying space theory. It's like classifying functor theory. And not every map can be pulled back from a universal one, but if it's Cartesian, it can. So if you go on to study topos theory, you'll, this will arise all the time. So I want to talk maybe in the last few minutes just about one of the most useful types of infinity categories that exist, namely the presentable ones. So was hoping to get to bar back, but clearly not going to happen. After presentability, and well, oh, sorry. I was going to talk about bar back, but there's not time. But this allows us to define the notion of a junction, which I needed to use. So definition, and a junction in cat infinity is a map. I'll just call it Z to delta 1, which is Cartesian and co-Cartesian. So why is this a relevant notion of a junction? Well, if I can take C to be the fiber over 0 and D to be the fiber over 1, and then the fact that the map is Cartesian and co-Cartesian means that you have, well, the co-Cartesianness means that the map from 0 to 1 can be lifted to a functor from C to D. And the Cartesianness means that there's a functor from D to C that I'll call G. And it turns out that you can start writing down what this implies by the fact that these are Cartesian and co-Cartesian. You keep taking subsequent Cartesian and co-Cartesian lifts, you get all the unit and co-unit morphisms. I'll leave that as an exercise for you, but they literally just fall out. And well, adjunctions are, of course, incredibly important in all of category theory. They're maybe even more important in infinity category theory because you do more via universal properties, because hands-on constructions are much harder in general. But let me just say, so I wanted to define this because this makes it possible to define the subcategory of cat infinity, or really large cat infinity. So want to define a subcategory of, so I'm distinguishing between small infinity categories and large ones. Presentable infinity categories are large, even though they have small mapping spaces. They have all co-limits, so typically they won't have a small space of objects. So what it means to be presentable is really that it has a presentation. So one of the main theorems in the subject, which is sort of a higher categorical version of the usual presheaf characterization, is that the formation of presheaves is the universal co-completion. So if S is an infinity category, then P of S, that's presheaves on S. So in other words, functors from SOP to infinity groupoids, because that's our analog of sets, because that's what all the mapping objects are. They're infinity groupoids. This is the universal co-completion. So in other words, if I have some other thing, T is co-complete, then to give a functor which preserves co-limits from P of S to T should be the same as to give a functor just from S to T without any assumptions. And this map is just given by restriction along Yoneda. I didn't say what the Yoneda embedding is, but it exists obviously for simplicial categories. So you can use the Quillen equivalence to get it on quasi-categories. So yeah, so think of this as a very free construction, like a free abelian group type construction. Abelian groups have a sum operation, and that colimits are generalizing the sum operation. So you can be thinking that this is something like abelian group or abelian monoid theory. And the real utility of presentable things, which I guess I will just have time for the definition of presentable. I'll say that really quick, and then I'll stop because I realize I'm out of time. But is that there is a tensor product, and the tensor product behaves, it has the same universal property as it does in the world of abelian groups. And you can do a lot of really cool higher categorical algebra if you use the tensor product on presentable infinity categories. And algebra naturally gives you presentable categories. Like if I take rings, that's presentable, modules, again, presentable, etc. Okay, so let me just give you the definition. I mean, the moral is that a presentable category is a category which has a presentation. So let's just see what that means. An infinity category C is presentable. I should really say a small presentation if there's a small simplicial set. Oh, I'll just say small infinity category S and a left adjoint presheaves on S to C, which will be essentially surjective. So this is like saying that it has small generators. Such that, well, we need to talk about what the relations are. The right adjoint C into this is fully faithful. So you're getting C as the local objects inside of P of S. And the small relations is just that this functor R preserves, well, I didn't say what this is, but kappa filtered colimits for some cardinal kappa sufficiently large. So that's the smallness of the relations. And anyway, this just gives you a beautiful category. I just want to say one more thing. The main theorem here is the adjoint functor theorem, which just says that a functor of presentable infinity categories, so F from C to D, is a left adjoint if and only if F preserves colimits. So the morphisms are just colimit preserving functors, and among presentable categories, they're automatically left adjoints. So this gives you this duality between the left adjoint version of presentable infinity categories and the right adjoint version. And then you get all these interesting relations between tensor products and internal Homs, and it's a very beautiful theory. But I will stop here. Thank you for your patience.
Let's thank David for the great talk.